Thanks. Well, good evening, ladies and gentlemen. My name is Eric Priest, and I'm delighted to welcome you to this James Gregory lecture on science, religion, and human flourishing on behalf of myself, Andrew Torrance, and Judith Wolfe over there. And I'm especially pleased also to welcome Anne Dyer to join us, who's the new Bishop of Aberdeen, we were really pleased about that news. And we also have a former moderator of the General Assembly with us too, so that's great. James Gregory was a key scientist in St Andrews in the 17th century. And you can see details of him on the two banners that are just outside, and also on the walls that are one floor up that you can get to either by going out of the back entrance or going up the stairs outside this lecture theatre. I'd be grateful if you could fill in the questionnaire at the end of the lecture, and also any of you who don't receive emails about these lectures, if you fill in one of those and put your email and name on it, then we'll make sure you get put on the list. Now, today's lecture is by Joe Penberthy, who is a key part of a wonderful transition that's taking place within the Anglican Church in the United Kingdom. So that's the Church of England, the Church in Wales, and the Episcopal Church of Scotland. The first women priests were appointed 20 years or so ago, and now 50% of the new priests coming every year are women. So that's a wonderful change. And Jo is the first woman bishop in the Church of Wales. She was appointed last year, and she's bishop of our sister town, St David's, in Pembrokeshire. There's Pembrokeshire, the southwest corner of Wales, and there's St David's, a little tiny town, tiny city, I should say, there. And this was, of course, where St David, the patron saint of Wales, where it was a pilgrimage site. He was a bishop there in the 6th century. And there's also a magnificent cathedral there, St David. There's a magnificent cathedral there. I thought you'd like to see a picture of this, because fortunately it did not fall into disrepair in the Reformation, after the Reformation. So they're lucky to be able to enjoy it to this day. The title of today's lecture is Learning the Lessons of Quantum Mechanics. So please give Bishop Joe a warm welcome.
Thank you very much. Thank you for the introduction. St David's Cathedral survived the Reformation because the canons of the cathedral there stole the body of Henry VIII's grandfather from a church in Carmarthen and buried it in the cathedral just to make sure that it would not be ransacked, and it worked. Very canny. So thank you very much for your invitation. I'm honoured, and I feel somewhat of a fraud, being as I'm neither a professional theologian nor a scientist, not even by background. My formal learning in science finished in 1976 with my 3 O-levels in physics, biology and chemistry, alongside a maths O-level, which was accompanied by, and I'm sure you'll be delighted to know, an additional certificate in calculus and coordinate geometry. I was pressed by my then physics teacher to take physics at A-level, not because I was a budding physics genius, but because I was a girl. And in the 1970s, schools were keen to encourage girls out of the so-called soft world of the arts and into the sciences, but my sights were fixed elsewhere. So while my formal learning in the science is finished in 1976, my formal learning in theology still continues. But as someone who's been in orders and therefore preaching and teaching the Christian faith since 1984, I would consider myself a practicing theologian, all with small p's and t's. And as a bishop, I'm someone who now holds the teaching office in the church, so I'm a theologian of sorts. but I'm far more used to pulpits, Bible studies and adult education groups than I am to giving lectures. So I crave your indulgence, and I seek to evade charges of fraudulence by my honesty. So I'm here not to give you the benefit of my incredible wisdom, knowledge and expertise, but to take you on a journey of exploration, exploring a case study in theology and science. In 1987, Pope John Paul II gathered a group of scientists, theologians and theologian scientists together at his summer residence in Rome for a study week on the theme of our knowledge of God and nature, physics, philosophy and theology. The week marked the 300th anniversary of the publication of Newton's Philosophiae Naturalis Principia Mathematica. When the papers presented at the conference were published the following year, Pope John Paul II contributed a preface to the book, and he wrote, "For the truth of the matter is that the Church and the scientific community will inevitably interact. Their options do not include isolation. Christians will inevitably assimilate the prevailing ideas about the world, and today those are deeply shaped by science. The only question is whether Christians will do this critically or unreflectively, with depth and nuance, or with a shallowness that debases the gospel and leaves us ashamed before history." Pope John Paul was reminding us that theology and science is not a niche pursuit for those who happen to be interested. Open-eyed awareness of modern science is an inescapable call for Christians who wish to live their faith as adults. Studying theology in the context of modern science is inescapable for those of us who are called to resource and equip them. Modern science, both its theory, its practice, and the technology it enables, is an inextricable part of the foundation and scaffolding of today's world. And so the study of theology and science is, as Pope John Paul reminded us, not something we can evade. The only question is how well or badly will the church do it? And I realise that here I am on this score preaching to the converted. As I've said, I'm neither a professional theologian, neither a theologian scientist or a scientist. I'm here not to regale you with my learned findings, but to take you on a journey, my journey, into a small part of this theology science territory. My journey began with a book published in 2006 by one of the most consummate scientist philosophers of recent times, On Physics and Philosophy by the late Professor Bernard d'Espagna. D'Espagna was a professor of physics at the University of Paris-Orsay, where he'd been director of the Laboratory of Theoretical Physics and Elementary Particles from 1970 to 1987. And it was his book, On Physics and Philosophy, that sparked my interest. It's a book about philosophy and a particular aspect of physics, quantum physics. Quantum physics, according to Wikipedia, is a fundamental theory in physics which describes the smallest scales of energy levels of atoms and subatomic particles. Specifically, it was d'Espagna's fascinating and, to a non-physicist, utterly baffling contention, a contention that On Physics and Philosophy he explores in depth, that while to all intents and purposes in the everyday world in which we operate, in the conceptual world in which most science is done, the common sense notion of local reality is true, or perhaps more accurately is a reliable assumption. But in a series of quantum mechanical experiments by Alain Aspect and his team at Orsay in Paris in the early 1980s had demonstrated, and here I quote, the discovery of non-locality. Non-locality, I was absolutely mind-blown. What on earth is that? What does it mean? In what sense is the world, reality, non-local? And if this is true, and the world or some part of the quantum domain is non-local, does that mean that our senses are out of kilter with the underlying reality? For theologians, there would be a definite, huge theological implication if God had created a world in which we cannot trust our senses. In his opening chapter, d'Espagna notes that philosophers have not yet caught up with what quantum theory and the experimental findings in the quantum domain are telling us. He writes, "Some philosophers do still make unrestricted use of classical notions of quite a general nature, such as locality, distinguishability, etc., taken to be obvious since Galileo and Newton's times. Most of them do so without realizing that the domains of validity of such notions are known nowadays to be severely limited." If this is true of philosophers, it is surely true of theologians. To what extent have theologians realized that the domain of validity of seemingly straightforward notions as locality, distinguishability, are, according to some physicists, now severely limited? If these domains of validity are severely limited, what might it mean for how theologians talk about the world in which we live and about the purposes of God, whom the Christian faith contends created it? It was these questions that I set off on a fascinating quest to explore. In this lecture, I will set out firstly why de Spagna believed, and here I am quoting, "non-locality will certainly remain true, even if one day the quantum formalism has to be replaced." Secondly, I will explore to what extent other quantum physicists agree with him, because not all do by any means. And thirdly and finally, I shall suggest what the relevance of this debate amongst physicists might be for Christian theology. And I offer this as a case study, as an example of how the relevance of a particular aspect of modern science for theology can be reflected upon critically and with depth, as Pope John Paul suggested. So, why was de Spagna so sure that quantum mechanics demonstrates the non-locality of some aspects of underlying reality? And I ask those of you who cannot quite naturally imagine what non-locality means to take this on trust for a moment. The crux of the matter for de Spagna were the results of a series of experiments published in 1982 by a team from the Institut d'Optique Théorique et Appliquée based at Orsay in France, led by the experimental quantum physics Alain Aspect. Similar experiments had been conducted since 1971 by others, but the experiments conducted by Aspect and his team are generally held to be definitive. So, what were the Aspect experiments testing, and why? And why did de Spagna find them so compelling? And I apologise to those here who are much better acquainted with these matters than I, but for the sake of those for whom this is new, I shall outline the background to Aspect's work. So, what was Aspect doing in the Orsay experiments and why? The experiments were quantum mechanical experiments, and to explain that what they were about and why they were being conducted, we need to give a short excursus into the development of quantum theory. With the benefit of hindsight, quantum physics began with Max Planck, who suggested a resolution of a long-standing problem in classical thermodynamics by postulating that energy released from a body radiating heat was not infinitely divisible. And he termed the smallest quantity in which such energy could be released the quantum of action. In 1905, Albert Einstein applied Planck's words to light, postulating the existence of photons. And in 1913, Niels Bohr applied Planck's work to Rutherford's work on the atom and produced a model that accounted for the line spectrum of hydrogen. It proved impossible, however, to extend the Bohr model of the atom beyond the hydrogen atom to atoms with more than one electron. And it was Werner Heisenberg who in 1925 broke the impasse by writing his famous paper that gave birth to quantum mechanics by giving up trying to work what was going on inside the atom and proposing a formulation that was based only on quantities that were experimentally observable in practice, namely the energy emitted by an excited atom. It was both highly successful and completely counterintuitive, in that the equations Heisenberg used in his calculations included not only the energy level in which an electron emitting irradiation began, but also the energy level in which it ended. And this meant that while reliable predictive calculations had become possible, it was impossible to give a credible account of the emission process across time, given that both the final and the initial states were needed for the calculation. How did the electron know it was going to jump to? Furthermore, Heisenberg's calculations were non-commutative, meaning that the order in which the steps of the calculations took place was significant. A different order would mean a different result. And when assessing Heisenberg's 1925 paper, Max Born recognized the usefulness of a mathematical tool called matrices, and with Pascal Jordan and then with Heisenberg, developed Heisenberg's initial idea into matrix mechanics. It worked, but it was phenomenally complicated. So 2 more versions of quantum mechanics were soon developed: wave mechanics by Erwin Schrödinger and transformation theory by Paul Dirac. Initially, it was hoped that Schrödinger's wave mechanics, unlike Heisenberg's matrix mechanics, described the underlying reality of quantum processes, although Schrödinger was aware from the beginning that when his paper was published, that his equation didn't describe a physical wave in 3n-dimensional space. But it was Born who showed definitively, to the dismay of some, that Schrödinger's wave equation didn't describe anything physical, but represented a probability wave. i.e., it told you the probability of what would happen when you did a certain equation. So soon Heisenberg's matrix mechanics, Schrödinger's wave mechanics, and Dirac's theory were seen to be equivalent mathematically. Despite quantum theory's success and despite the part he'd played in it, Einstein was never reconciled to it. And his disquiet led to the publication in 1935 of a co-authored paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete?, known for short as the EPR paper. Einstein and his colleagues were not satisfied with a theory that, however successful at predicting the results of experiments, could not describe adequately the underlying reality the predictions described. And as the paper's title says, the authors set out to demonstrate the incompleteness of quantum theory by pointing out a contradiction between 2 logical deductions based on premises drawn from the theory. As Bohr recalled later, Pauli initially thought that Einstein and his co-writers had proved that quantum mechanics was not complete. 5 months later, though, Bohr published a response which, for many quantum physicists, successfully answered EPR's point. Not everyone was satisfied, and discussions rumbled on. If the EPR paper was correct and quantum theory was incomplete, how might it be completed so as to be able to describe the underlying reality, the quantum world, rather than just predict, although very successfully, the results of quantum experiments? Many whose instincts were with Einstein and with Boris Podolsky and Nathan Rosen, the co-authors of the paper, had been halted in their tracks even before the EPR paper by John von Neumann's 1932 proof that a dispersion-free, i.e. an exact description of quantum reality was impossible. And the general environment of university physics departments was to leave such underlying questions alone and to get on with the physics. Or in David Merman's famous phrase, usually but mistakenly attributed to Richard Feynman, shut up and calculate. Even though, in 1952, 2 papers published in Physical Review by David Bohm had put the question firmly back on the table. Bohm had put forward a dispersion-free or exact account of quantum theory. As the CERN physicist John Stuart Bell later said about Bohm's paper, I saw the impossible done. In these 1952 papers, Bohm had shown that a further description of the reality underlying quantum mechanical results was theoretically possible. But this raised a significant problem. Given that by 1952, no one believed that the predictions of quantum theory would ever be falsified by experiment, it followed that as if any theory had been derived as Bohm's had been to complete the existing formulation, must make the same predictions for quantum experiments as the existing theory did. And if that's the case, how on earth would it ever be possible to decide between them? And this question is the context of the aspect experiments. The CERN physicist John Bell, who'd been so struck by Bohm's 1952 papers completing quantum theory, first considered the question of how Bohm's formulation of such a theory could be possible, given von Neumann's 1932 proof that it wasn't. Bell submitted a paper to the Review of Modern Physics demolishing von Neumann and other proofs against the completion of quantum mechanics, and having done so, turned his attention to finding a way of discriminating between theories like von Neumann's that would complete quantum mechanics and between the predictions of quantum theory. Bell noticed a feature of Bohm's theory that was not consonant with the theories of classical physics. We've mentioned it already, and wondered whether this feature was a necessary feature of any theory that attempted to complete quantum theory. That feature, Bell called it grossly non-local, since the guiding equation in Bohm's theory affects the positions of all the particles instantaneously wherever they are. Was this a necessary feature of any theory that attempted to complete quantum theory? So Bell managed to formulate an equation based on the assumptions of causality, but also respecting the restriction of locality, i.e. that nothing travels faster than the speed of light. He formulated an inequality that made different predictions for a particular set of experiments over a particular set of measurements. So that if nature obeyed local causality, the results would be within a particular set of mathematical parameters. And if they didn't, then Bell's inequality would be violated. Everybody was very excited at the possibility that, well, those people who cared were very excited about the possibility. Most physicists were just getting on with doing physics. But at the end of Bell's paper, he says it doesn't take much imagination to imagine that this experiment can be conducted. Well, it took 5 years before somebody who knew about experimental physics as opposed to theoretical physics managed to develop an equation that was actually testable in practice. And then it took another year to actually set up the mechanics of actually doing the experiment. And the first experiment was done in 1970. In his 1964 paper on the Einstein-Podolsky-Rosen paradox, Bell first describes the experiment and derived the standard quantum mechanical prediction for such an experiment. And then he formulates the mathematical expression that the experimental results had to obey if they could be considered consonant with the requirement of local realism. And it's known as Bell's inequality. Inequality because unlike an equation where the various terms in the expression are related by an equals sign, in an inequality, the terms are related by a greater than or less than sign. The experiment that Bell chose had originally been proposed by David Bohm and Yakir Aharonov when they were seeking to prove whether or not one of the features that Einstein predicted would actually happen in practice. Bell took that experiment. It was an experiment proposed on spin 1/2 particles in the singlet state. Those particles are said to move in opposite directions, and the spin of one would be tested at one end of the experiment, and the spin of the other would be tested at the other end of the experiment. And measure in quantum physics is a very delicate term. And Bell is very careful to write his paper saying registered, because to say measure is to make an assumption that what you're testing exists before you test it. And that's not an assumption that everybody is keen to make. So Bell was very careful when he wrote his paper to talk about what would be registered in the classical instrument rather than what was going on underneath. So nevertheless, in Bell's proposed experiment, he still does speak in sometimes of spin measurements on a particle, but he's clear that what counts as significant in the experiment is what is registered by the instruments at either end. Spin, although it sounds as if it's going round and round, doesn't have a classical equivalent. It can be registered in 3 orientations, x, y, or z, and the particles in the singlet state are in pairs, meaning that however far away the particles are from each other, a measurement on one, if it registers, say, z minus 1, will always register on the other one in the pair as z plus 1. So whatever it registers in one particle, it will register in the same orientation, but directly opposite in the other. And Bell makes the point that his inequality encodes the mathematical relationship that would have to be true if, as would be the case in deterministic classical physics, the setting of one magnet doesn't affect the outcome of the other. Thus, Bell's inequality offers a way of experimentally discerning whether or not the quantum domain is locally causal. The experimenters who finally did the first experiment that was considered definitive were John Friedman and John Clauser. And their experiment violated Bell's inequality, i.e. Was outside the domain of the results which would have to be respected if what was being measured was locally causal. Nobody was surprised because nobody expected that the predictions of quantum mechanics would be violated, but some people were really, really, really disappointed. At the end of his paper, Bell had said that you'd have to be really, really sure, you'd have to make sure that during the time between the emission of the particles and the registering of the spin direction, that the magnets, the analyzers, were changed in flight. And it was Alan Aspect that actually managed to do that with his team in Paris in 1982. And that's why those experiments were held by one section of the quantum physics community to be absolutely crucial. Quantum mechanics was right, Einstein was wrong, or if Einstein was right, any other theory that completed quantum mechanics would have to be non-local. So D'Espagna believed until his death that the quantum world had aspects of non-locality. The only way out of it, as far as D'Espagna is concerned, is if there is no free choice for experimenters, i.e. superdeterminism, if we don't have any choice about what we do, even though we think we do. And that is a let-out, but nobody really wants to think they live in a world where everything is superly deterministically set out. People who, especially who do experiments, like to think they're choosing what they're experimenting on. So as far as D'Espagna was concerned, superdeterminism is the only way out of making the deduction that the quantum domain features non-locality. But not everyone in the field accepts this. So for theologians to understand what that might mean, it's first important to drill down into what the whole spectrum of the quantum physics community is saying about these experimental results. Now, the first problem is that not everyone accepts, even though the experiments are fairly conclusive, utterly conclusive, that Bell's inequality has been violated. And therefore, any talk about their violation is a non-problem. The first set of people who think that that's the case is those who think that Bell's original inequality is entirely meaningless, because Bell has derived it using algebra based on Euclidean geometry, a geometry that absolutely doesn't model all aspects of the real world. As an example, Dr. Joy Christian points to the problem that Euclidean geometry poses for those who design computer animations or aircraft guidance systems, given that it cannot model the 6th degree of freedom of movement that we have in real space. So if the algebra Bell used in his inequality cannot model the real world, how can its violation, says Joy Christian, be used as the overthrowing of common sense notions like time and space? So, D'Espagna says the aspect experiments means the world is non-local. Dr. Joy Christian says Bell's maths is wrong, so therefore you can't build anything on any experimental results. He's not the only one that thinks you can't believe the experimental results. The late Caroline Thompson, is a statistician, looked at the way the raw data from the experiments had been used and says that that raw data didn't bear out the weight of the interpretation that the scientists had been placing on them. Others think that Bell's inequalities has not been violated because of various inexactitudes in the experimental methodology, known in the literature as loopholes. And they therefore conclude that the results are not beyond reasonable doubt. Loopholes refer to the possibility that data may be skewed because of experimental deficiencies. And closing those loopholes is the main thrust of current experimental research in the area. Some loopholes, as we've said, are impossible to close. Freedom of choice loophole. Every experiment has to make the assumption that we are free to choose the experimental parameters. And recent experiments have set out, though, to close the freedom of choice loophole as far as possible using the light from Milky Way stars to set the parameters in the detectors. Or the most recent experiment, one done this year, used the inputs generated from people across the world using computer games to determine the settings of the instruments. The other main loopholes considered in the literature are the efficiency loophole, the fair sampling loophole, and the locality loophole. In the case of the efficiency loophole, the problem may arise because of the inefficiency of the detectors. The fair sampling assumption means that the particle pairs that are registered in the experiment and from which conclusions are drawn simply are not representative of the whole sample. And the locality loophole means that the detectors are not far enough apart to preclude one influencing the other. The final group that don't think the experimental violations of Bell inequalities mean anything about the world, even if the experiments are perfect, are those who are adherents of the many worlds interpretation of quantum mechanics. And the philosopher of science David Wallace explains, there's a tacit premise in Bell's argument that the results of measurements actually have definitive outcomes. This looks pretty innocuous, because if measurement results are macroscopic, of course they're definite. But of course that is exactly what the Everett interpretation of quantum mechanics denies. Or more accurately, measurement outcomes are relative to a branch. And branching, because it's just a dynamical process, namely the process of decoherence, is a local effect and spreads out at light speed. So if I'm at one end of a Bell-type experiment and you're at the other, I won't be able to ascribe any definite outcome to your measurement until the branching caused by that measurement has reached me, and that happens at light speed. So many world adherents think that all the possible outcomes of a Bell experiment do happen, but you, the experimenter, only experience one of them. So you can't make any further deductions from your result because all the other results have happened as well. That being said, most physics and philosophers of science working in the field do accept with d'Espagna and with Bell himself that the testable versions of his inequality have been violated by experiment. But what follows? The first question that follows is not what does it mean? I mean, theologians love to jump straight in there with what does it mean? But the first question is to what field does it apply? What's the field of its significance? We've already seen Joy Christian says it doesn't actually mean non-locality because the algebra doesn't relate to the real world. And that was something that was seen a long time ago. So maybe Bell's inequality is just another demonstration that other geometries are useful. However, the majority in the field think that its field of significance is the world in which experimental results happen. But not all agree. People other than Joy Christian think it's a result to do with probability theory. how probability applies to experimental results in classical physics cannot be assumed to apply to experiments in the quantum domain. And a member of the very, very first team to carry out an experiment to test a Bell inequality, L.R. Kasday, made this point in 1971. And it's been rediscovered subsequently by a number of scholars, for example, Arthur Fine and Andrei Krennikov. And Krennikov has noted that the Russian mathematician N.N. Vorobyev formulated this in 1962, 2 years before Bell published his inequality. And the philosopher Itamar Petowsky pointed out that Bell's inequality is a restatement of Boole's condition of possible experience, and its violation therefore shows that Boolean logic is inapplicable to quantum theory. So to recap, testable versions of Bell's 1964 mathematical expression, known as Bell's inequality, have been repeatedly violated by experiments. While some thought that the statistical methods were not rigorous enough to be certain that the inequalities had been violated, others think that the loopholes in the experiment preclude any conclusions being drawn. The majority do consider the violation significant, and the majority, even though some think it's about probability, the majority do think it's significant for our understanding of the quantum world. So, if you think it is significant for the quantum world, what happens next? D'Espagna thinks it means that some aspects of the quantum world are non-local, but not everyone agrees with him. There are other assumptions people think that Bell based his inequality on, not just local realism. So before it can be decided which of the assumptions has to be dropped, which assumption doesn't apply to the world, you first of all have to catalogue all the assumptions that Bell can be said to have used. There is a huge literature that has grown up discussing this. Some of the assumptions are analogous to the loopholes. For example, the fair sampling assumption. If experimenters are aware that their design does not close the fair sampling loophole, then their experiment has to rely on the fair sampling assumption, i.e. that the tested pairs are a representative sample of the entire, the pairs that register are a fair representation of the entire sample. The no conspiracy assumption assumes that the measurement settings of the detectors are independent of the microstate of the system being tested, and that the choices of the experimenters as to which direction of polarization or spin is measured at each detector are not correlated with the microstate of the system. The fair distribution of total microstates assumption means that the distribution of microstates in the ensemble depends only on the macrostate, and no matter which pair of compatible observables are selected, for any sufficiently long run of joint measures, the microstates on which the measurements are effectively performed are representative of the same general distribution. There are no arguments in the literature that this is the assumption responsible for violation. Another assumption that Bell made is that there's no such thing as backward causation. Again, in the classical world, that seems obvious, but in the quantum domain, there are physicists who deny it. For example, in 1986, John Cramer outlined his transactional interpretation of quantum theory on the assumption that backwards causality happens within quantum interactions, and he is still continuing to develop and test that model. While Hugh Price, on the other hand, developed a model in which events could influence events in their former light cone. One of the major assumptions that underpins Bell's derivation of his inequality is that of realism. And in the context of this discussion, realism is an umbrella term, meaning that the outcome of a measurement is not created by the measurement, but corresponds to properties possessed by the measured system prior to the measurement. And this assumption has got a whole lot of different names in the literature: realism, determinism, causality, property definiteness, and counterfactual definiteness. Counterfactual definiteness is a strong version of realism, meaning that not only are there existent causes for experiments that are actually performed, but also for all possible experiments that could be performed on an individual system, no matter whether any experiment or which experiment is actually performed. And Sir Anthony Leggett's version of this assumption is macroscopic counterfactual definiteness, meaning that the hypothetical outcome of measurements that were not in fact performed can be treated as fixed facts about the world. There are also definitions of realism that don't include ascriptions about what the results might have been in experiments that were not performed, and a famous paper by Asher Perris expounding this was entitled "Unperformed Experiments Have No Results," but he demonstrated in that paper that in a Bell-type scenario, the counterfactual reasoning could not apply, but he goes on to say that this means that locality has to go rather than realism. And as we've seen, many worlds theorists believe that when a quantum measurement is performed, branching takes place, and therefore there has to be a further tag to the realism assumption that Bell made, and that's that reality is single-valued. Each measurement has only one actual outcome. And then we go to where we started, non-locality. And that's the one that most theologians who read in the area and write in the area think is the one that has to be sacrificed, the one that de Spagna thinks has to be sacrificed. You remember that what started me on this journey was de Spagna's starting claim that the aspect experiments had discovered non-locality. What it means to assume locality in experiments designed to test inequalities, it's much discussed. And just as we saw, there are many versions of what realism is, there are many versions of what locality and what non-locality is. So while de Spagna and others passionately believe that the violations of Bell inequalities mean that there is in the quantum domain some aspects of non-locality, we've seen that others in the field think that one of the other underlying assumptions Bell has made is the one that has to be sacrificed if we're going to describe the quantum world properly. Time runs backwards, unperformed experiments have no results, the particles, in inverted commas, do not exist until the experiment happens, or, with de Spagna, aspects of the quantum world are non-local. Still others, cubists, believe that Schrödinger's equation doesn't describe the world, but simply tells me what will happen when I conduct experiments. So, how do physicists and philosophers of science decide which of those options are true? What actually does account for the experimental violations of Bell inequalities? What are they telling us? There is no consensus on this amongst mathematicians, physicists, and philosophers of science. So the experimental results and the theories behind them do not lead definitively to any one particular interpretation of them. It all comes down to choice. After 50 years of sustained thought, discussion at conferences, forests and forests of published papers, after nearly 50 years of planning and running experiment after experiment, the answer to the question of which of the assumptions cannot be said to hold in the quantum domain remains a choice. Not a simple choice, but a choice nevertheless. And in my view, this is, for theologians, the most significant thing to emerge from the field of Bell scholarship. What the results of these experiments mean in this most stringent of scientific disciplines, in the end, comes down to the personal choice of the scholar. Don't misunderstand me. I'm not saying it's airy-fairy. It's not a random choice. It's a choice made in concert with the scholar's most deeply held convictions about the nature of the world itself or the nature of the scientific enterprise. It's not a choice without reference to facts, but the facts in question do not determine how they should be interpreted. The facts in question, Bell's 1964 paper, and the experimental results of the experiments conducted to test a Bell-type inequality do not compel a particular interpretation. The choice of which interpretation of the Bell's paper and of its experimental consequences by those who hold that they are significant comes down in the end to a personal choice that depends upon a scientific or a philosophical instinct or upon a belief as to how the world is or has to be. So despite my initial excitement about the world's non-locality, having looked at this small area of debate in quantum physics very closely, it emerges that the first datum given from it for theological reflection is not the discovery of non-locality necessarily, but the inescapability of choice. The only thing that can definitively be said about the experimental violations of Bell inequalities is that we have to choose how to interpret them. There is no privileged place from which an uncontested choice is possible. We are not granted a putative access to a God's eye view, which will give us a place beyond our world of experiments and theories and ideas, which will give us a place beyond from which to make a definitive, final and uncontestable decision about what is true in this area of physics. Even in this hardest of hard scientists, certainty is denied us and choice is inescapable. So what theological resources are there for theologians reflecting on this aspect of science where choice is unavoidable because there is no secure possibility of an outside standpoint from which the unassailable truth of the matter can be discerned, but where this lack does not imply anything goes or subjectivity? It isn't a question of going eeny, meeny, miny, mo, I prefer that one. Each choice is made on secure, scientific, philosophical, defendable grounds. But there are other equally secure, philosophical, scientific, defendable grounds on which to reach another choice. So how can the interpreting of the experimental violations of Bell's inequalities be read theologically? The irreducibility of choice is one, but it's not the only fact to emerge from this area of study. 50 years of thought, experimentation, discussion based on this one small 5-page paper has not led to the right answer, but it has led to new thinking, new technology, new fields of research and application. There is no one secure right answer, but possibilities for fruitful thought and action, technology and experimental action remain. Unassailable truth is not available to us, but making a decision and acting upon it and seeing what happens is. We plunge in, we make a choice with no guarantees, and we find out as we go along whether our choice is fruitful or sterile. Physicists and philosophers of science make a choice about how to interpret the violations of Bell inequalities, and they push work, theoretical and experimental, further on that basis. Other physicists, other philosophers of science make other choices, develop other work, and in different directions, sometimes opposing ideas, also each produce fruitful work. The paper was written because Bell, with Einstein, believed that quantum theory was incomplete. Quantum cryptography was vastly developed when Arthur Eckhart produced his paper that assumed that quantum theory was complete and worked out what Bell's inequalities meant on that basis. So this too is a datum offered for theological reflection by this small area of quantum physics. Not being able to hold on to a definite truth doesn't preclude fruitful thought and action. Many of you will say, well, this is merely the scientific method as Robert Boyle and the Royal Society developed it, when it had become clear that metaphysical certainty was no longer tenable, and I think you are right. But it's surprising how many scientists are affronted, and theologians, are affronted by what they see as science's failure to deliver an unassailable account of what quantum theory means, as opposed to being able to use it incredibly fruitfully in all sorts of amazing ways. Sean Carroll, for example, calls it embarrassing. Theological reflection on the data offered by all that has sprung from Bell's small paper can spring from holding together these two perspectives. The overview that says there's not one right answer, but a dazzling reality of oppositions on the other hand, with the possibility of plunging in and taking sides. Reflection on the irreducibility of a myriad of conflicting answers underlines to us the restriction of our situatedness, our creaturely limitedness, while the fruitfulness for new thought, new fields, new technology, new applications demonstrate in a way that is not at the least paradoxical the vibrant possibilities of that same limited creatureliness. That 50 years of thought, experimentation, discussion based on this one small paper has not led to the right answer, but to myriads of new thought, new technology, offers itself as a lived expression of what it is to be a creature. And it's important to be clear what I'm not saying here. I am not moving from reflection on this area of science to a theological conclusion that therefore we are creatures. I'm going in the opposite direction. The irreducibility of the interpretations of Bell's inequalities does not lead to the theological conclusion that we are creatures. But if one starts, as a theologian can, with the presumption that we are creatures created by God, then we can reflect fruitfully on what we see emerging in this particular area of physics. And that can be done not merely from a theological standpoint. The concept of immanence, developed by the atheistic 20th century philosopher Deleuze, is another such standpoint. So I'm not suggesting that the impossibility of knowing the right way to interpret the violations of Bell's inequality compels a theological conclusion, but I am suggesting that from the perspective of the Christian notion of createdness, the irreducible plurality of interpretations of the violations of Bell's inequality and the richness of conflicting and contradictory interpretations alongside a plethora of technological and experimental expertise offers us a parable of what it means to be created. St. Gregory of Nyssa, a 4th century church father, the youngest of the Cappadocian theologians, is a good place to start for theological reflection on being creatures. St. Gregory was clear that in our thinking, as well as in our being, we cannot escape the reality of our situatedness, our createdness, and therefore the reality of the boundedness of our being and our thought. Gregory begins with the assumption that all that is stems from the creative will of God. And unlike the Neoplatonists, St. Gregory contends that all that is, including human life and thought, are bounded and situated within what he calls a distema, a Greek word which at root means interval. But only translating it as gap or interval doesn't capture its sense of extendedness or movement. Distema is the determining feature for Gregory of the created order extended in time and space, moving from beginning to end. Creation is inherently diastemic. Diastemic in that it's set apart from God. It doesn't sort of emerge from God. It was created by God as an integrity in its own right. But gap, interval, extension is part of what it is. And it's positive. Diastema makes the life of creation possible. It expresses the ontological distinction between the creator and the creation, but it also indicates the nature of what is created. And in this context, it helps us explore both the scope of what it is possible for human thought to grasp and the nature of that thinking. Gregory of Nyssa maintained a resolute commitment to the inescapable reality of ontological distinction between creation and creator. There is no outside standpoint from which to decide which of the interpretations of Bell's inequalities is right. But St. Gregory's understanding of what it is to be a creature also means that we are given the possibility of action and thought within the creation in its limits. So both limits, the denial of ultimate truth, but the almost endless possibility. Because if we cannot know what the truth is, we are not bound by the nature or the reality of the truth. We can endlessly experiment, we can endlessly develop, we can endlessly push. In Philip Hefner's evocative phrase, we are created co-creators. We are denied access to the one meaning of the experimental violations, but they become thereby both theoretically and practically redolent with possibility. Gregory's sense of the constructed nature of human language and thought is taken up by James K.A. Smith, a modern theologian and a self-confessedly conservative Christian. Smith makes no reference to Gregory, but he holds that we are creatures created by God in the midst of a total reality, also created and upheld by God. And exploring the reality of this for him means appreciating contingency, finitude, and dependence. Like Gregory, he recognises that our thought and language cannot escape the limits of our creaturehood, and this has implications for what it is possible or impossible for human beings to know. Just as Gregory sees the fact of dystema as the very condition that makes human cognition and language possible, as well as the boundary beyond which they have no purchase, Smith sees interpretation as not only inescapable but positive. Smith's work therefore holds out a promise. Taking the stance that interpretation is not a fault or a flaw, something from which to flee, something to be overcome, Smith creates a space in which the plurality of interpretations of the experimental violations of Bell's inequality can be seen not simply as inevitable because of our lack, but a good, a resource for creativity and not a problem to be tackled. Like Gregory, while believing passionately in the God and Father of our Lord Jesus Christ, Smith denies the possibility that human thinking can inhabit a God's eye view. Smith's work on 20th century philosophy, seasoned with his conservative Christian faith, has resulted in a deep reflection on what it is to think and act and speak as a contingent creature. And he criticises the move that theologians make to stake a claim on absolute truth. He writes, "The move to stake a claim on absolute truth is a symptom of a deeper theological problem, an inability to honour the contingency and dependency of our creaturehood. There might even be something rather Gnostic and heretical in this failure to own up to contingency. Indeed, one could argue that the claim to such absoluteness is at the heart of the first sin in the garden." So, Bell's inequality has produced 50 years of thinking, experimentation by physicists, those who really aren't concerned about what it means, but want to know what it does. And theology, when we face the reality of our createdness, can accept that knowing the ultimate truth is something that is denied us. But that doesn't mean we do not have the ability to act within our own domain with all the fruitfulness of the resources that this creation offers us. There's more, but I shall stop now.